localization of a robot with PyBex. I have a robot, a 2D robot, which has to localize in a 2D environment. In this environment, I have 4 landmarks. So for the landmarks, I know their coordinates. They are given by this table. So for instance, the first landmark has coordinate 6 and 12. So the robot is able to measure the distances to the landmarks. So for instance, the distance to the first landmark is given with some given accuracy, and it is inside the interval 10, 13. It is also able to represent, so to measure the azimuth. I mean the angle made between the landmark and the robot. So this azimuth is given inside the interval, given in radian. Also, since I have 4 landmarks, I have 4 coordinates, 4 interval distances, and 4 interval azimuth. So the robot is here, for instance. Normally, so the coordinates will be denoted by P1 and P2. It has a heading, normally, but here we assume it knows it because, for instance, it may have a compass. And the mark, one of the mark is represented here, M. So here I will have M1. For instance, if it is the ith landmark, I should have put here I, and here I will have M2 of I. Okay. Now I measure some distances. So some distances can be, for instance, represented by this segment. This distance corresponds to d, let's say d of I, but it is also able to measure the azimuth. So what is the azimuth? The azimuth I have to represent here a direction, reference direction, which is horizontal here, and then I have the azimuth corresponds to this angle, so alpha of I. So I have some kind of uncertainty with respect to the distance. That's why I will obtain most of the time something which looks like an arc like this. Because of the interval with respect to the distance, but also an interval with respect to the azimuth. So with respect to the azimuth will be something like this, for instance. So it's not easy to see here, but here this corresponds to the interval distance, and this angle here corresponds to an interval azimuth, alpha of E. And of course, I have not only one landmark, but 4 landmarks. That are given here. So the set of all positions that are consistent with the ith measurements corresponds to the set of all P1, P2, such that we have a distance and we have a consistent azimuth, such that M1, M2 can be reached from P1, P2, uh, with a vector which corresponds with a norm d and an azimuth alpha. So first, what it asked here is to represent using a specific separator. So separator which is named seppolar x and y of pipex. We have to draw an approximation for the set pi for different I suppose, so maybe p1, p2 up to p4. For this, I will start with a Python program. So the Python program is named here pipex locpie, so loc like localization, and pi because what we have here, this kind of shape, which is the intersection between, so this kind of shape, which is the intersection between a ring and a sector, corresponds to what we call a pi. So for this, I start with a small program. The small program, of course, import pipex because I will use separators, interval, contractors, and so on. I will use numpy for mathematics. I will use vibes to draw a picture. So vibes is, of course, here. I have to start it first, here. And to go fast, I started with the marks. So the marks are represented by a list of with the coordinates inside. So here is the coordinates of the first landmark and the last landmark, which corresponds to what is given here. I have also a list with intervals for d, intervals for alpha for the azimuth. So everything is already entered in my program, which is given here. Okay, so first I will, if I want to draw a little, for instance, I will try to draw the landmarks. I will start with vibes. So I check everything's okay. I run it. Okay, it's okay. So vibes dot. So I will do a begin drawing. Then I will do a new figure. So vibes dot new figure, and I will call it, for instance, I will call it locpie, localization with npi. Vibes dot so set figure properties. Vibes but set figure properties. So here for x, I will take I will start at 100 pixels. For y, let's say also 100. The width will correspond, let's say, to 1000 pixels, and the height to, let's say, 700 pixels. Okay. So now, if once I have prepared my figure, I will do for m in marks. Then I will draw, for instance, a circle. So vibes dot draw circle. Here I will write m of 0, because remember that with Python everything starts with 0. Not like in mathematics. Normally I should have put in mathematic form start at 1 because of the x coordinate. Here I will have m of 1. Let's say the radius will be 0.5, something like this. And the color will be, for instance, yellow. Yellow inside and, I don't know, no, black inside and yellow in the border. So of course here it should be like this, and let me check here. It should be like this. I run the program, and if I look at vibes, I see my 4 landmarks that are given here. If I want them bigger, I will put 1. Okay. Now I will try to draw a pie, just to use the separator named seppolar xy. So to do this, I will go here and I will build a separator, sep1 for instance, I will call it, which is a separator polar xy, because I have another one which is named rho theta, but here I use xy. And I will write d, so the first distance, let me call it d of 0. It will correspond to this distance. And I will take also an interval for alpha. So I will take alpha of 0. Okay, so it will correspond to this one. So once I have built my separator, I will use a Civia to represent the corresponding paving. So I will do this here. Py Civia, which is everything is in Pybex. I will have to enter an initial box. The separator, let's say separator 1, and with accuracy 0.1. I have to initialize my box. Let's say here p equal, it will be a box, so interval vector. I will put here let's say minus 20 for the x component, and the same for y. So I have declared a separator, and the Civia will compute an inner and outer approximation using subpavings. Here it should be d, of course. And here I have a pi. So this pi corresponds to a distance to the origin between so it was an interval between 10 and 13, so this distance, and the corresponding azimuth, it was 0.5 and 1. So a pi can have different shape. Let's say if I change a little bit, so the interval here, and I put, let's say, for alpha 5, the pi, it is also a pi. So I come back to the initial interval for the azimuth, and now I will discuss about the transformation of a separator. So this separator, sep1, corresponds to a pi, and now I will show how we can make some geometrical transformation on sep1. So sep1 corresponds to a set. I will try to translate or to rotate it. To do this, I should define a function. So let's say f1. f1, it will be a function, ibex function, which is declared as this one. And to p1 and p2, I will return let's say a rotation. So a rotation will be cos, so of 1 radian. 1 radian cos 1 multiplied by p1 minus sine of 1 multiplied by p2. Here I will put everything between parentheses, and for the second coordinate I will write sine of p1. So it corresponds to rotation plus cos of rotation of 1 radian, cos 1 times p2. And for the transformation, so I will explain later, I also have to write its inverse. So is the inverse of f1 corresponds to, here it will have a plus because it is a rotation matrix, so I have to transpose it. If I transpose it, I will have minus like this. Excuse me, plus. The minus will be here. Okay. Yes. Now I will write, for instance, sep equal to sep transform. I will write here separator 1, the first one. I will enter the function and its inverse function, f2. And if f1 corresponds to a rotation, if f2 is the inverse of f1, then the new separator corresponds to a rotation of the separator 1. In the CVA, of course, I will have to write sep, so the new separator that has been built here. So here, of course, I close the parentheses, I run the program, and I obtain the rotation by -1. So it means that here it corresponds to the backward. So the reciprocal, I will call it backward. whereas this one is a forward. Forward, F forward, F backward. So I will put this in this way. Okay. Now let me explain how the separator transform works. For the transformation of a separator, consider a set, for instance this one, a pi, for which I have a separator, sep, let's say x. Here it is x1, here it corresponds to x2. I assume that I have a function f here, for which I have an inclusion function. I have also an inclusion function for f minus 1. The image by f of this pi corresponds to something that can be, for instance, something like this. Okay. Now I consider a box. Let's say this box. And from the separator I have for x, I want to build a separator for y. So here it corresponds to x. Here it corresponds to y. I take the black box here, and I will, by f minus 1, I will obtain, let's say, this box. This box. Now, from this, I will be able to call a contractor, inner and an outer contractor. It means that it is a separator, and I will be able to remove this part. So to represent what I've removed, okay, I'm able to remove this part, and I am also able to remove, for instance, this part, thanks to an outer contractor. I remove also this part. Then it remains to me a box which is given here. And this one. So I take the green box, and I will use the inclusion function I have for f, and I will obtain in the y space another box which will be bigger. So this one is corresponds to the image of the green box, and from this green box I will be able to remove this this part, and also this part, and it corresponds to what is done by the image of a separator. So to build a separator for y, I need first to have an inclusion function for f, an inclusion function for f minus 1, but also a separator for x. If I call this vector, the one that goes from M to the robot, if I call it, let's say V, I will have M, a little this, I will have M equal to P plus, so the vector V, which corresponds to D times cos theta, cos alpha sine alpha, and this corresponds to V. So I know that V corresponds to a pi. Now, of course, I can isolate like this. What is interesting for me is P. So P equal to the landmark M minus V. So from V I am able to go to P thanks to a function f. And the reciprocal of f, so this one is known. M is known. And I will be able to go from the reverse function will be V equal M minus P. So from this one, which is a pi, I have a separator for V. I will be able to translate it and to change its sign thanks to the function f, which is bijective, and this one corresponds to f minus 1. Of course, here I should have something which depends on E, and it will be also for V, which depends on E. So I will try to program this. I come back here. I have my forward function who have as input, let's say, V1 and V2. And the forward function will send me not this function, but so I will first write M equal marks of 0. I will consider only the first one to start. Here from I will associate the function we give me. So here I will put a float minus V1 here also a float minus V2, and for the float I will put M of 0, M of 0, and M of 1. So it will correspond to the first landmark. What about the backward? So backward will be almost the same. But the input will be now P1 and P2. And here I will have P1 and P2. So these two forward-backward functions correspond exactly to what I have written here. Here I have to put parentheses. I run the program, and I have here the set of all positions for the robot that are consistent with this landmark. Okay, so I have to do this for the second landmark. 1. I obtain this, and so on. So it answers the question given here using optimal separator, this one. Draw an approximation of the set Py. Now I have to try to be consistent with the largest number of data. So to do this, it means that probably there is some outliers. And of course, the last question asks me to find the outliers. So in this case, I will not have to perform an intersection of all the Pi, but a Q-relax intersection. Probably I will have to relax some of the intersection. So to do this, I will have to build a list of separators. Let's call it seps. seps, a list of it will be initialized as empty, and for here m, all distances, all alpha inside the corresponding array. So it will be marks distance alpha so this one I have to add a tabulation here. I will build my separator. This one, I will have the distance d and alpha. I don't need this anymore. I build my forward function, but here okay, and my backward function as previously defined. Then I will build this separator, which corresponds to a transformation as previously done, and I will append this separator to my list of separators. Okay, now I will build the final separator, which is bed by Q relax intersection. So sep Q intersection proj f. So here it's sep okay, it was this one. Okay, seps. Now I have to initialize a Q, the number of sets I want to relax, and the first will be 0. So it will perform a classical intersection. I run my program and I obtain the empty set. Immediately there is no solution, so I know that there is some outliers. Now 1. I obtain this set, so I mean I can be consistent with at least 3 of the landmarks. Okay, my landmarks are a little 0.3 is sufficient, the size. So now I will try to be consistent with 2 of them, just to vibes. So if I want to be consistent with the 2 of them, I am either here or here. So there is different strategy to feed the data. You can so each of the connected components corresponds to a group of 3 landmarks. So they disagree between this one and this one. I want to be consistent now with only one data. It will correspond to the union. Okay. So this corresponds to the union of the 4 pies. So of course, as we saw before, it was possible to be consistent with at least one. So we can guess here on the picture that I have 1 pi here, okay, 1 pi here, 1 pi here, and 1 pi here. This one corresponds to the last data. Of course, I can see that the 3, when I relax one, it will automatically relax this one. It means that the outlier corresponds to the false data. So let me check this. To check this, I will ask no q equal to 0. So no, and I remove the last one just to check. If I do this, I run the program and I obtain the same as before when I relaxed the last one.